I want to move on to a different topic now, and that is wave propagation. There are two different wave phenomena I'd like to deal with using Fourier methods. The first is dispersion, the second is diffraction, but first we're going to look at dispersion. So first of all, what do I mean by dispersion? Well, let's just think about the simplest wave we can imagine, a sine wave, and it's traveling through space and time. So a sine wave that moves in space can be written as sine kx minus omega t, and we can recall the speed of this wave is given by c, the ratio of omega and k. So here's our sine wave. It moves through space, but we know that if we start with a whole bunch of different sine waves, we can add them up to make any shape we want, because that's what Fourier theory tells us. We can do a Fourier sum or a Fourier integral and synthesize any pulse shape or train of pulses that we wish via a sum or integral of harmonic waves. So let's have a look at some really basic examples. Here we have just two different sine waves, harmonic waves of different frequencies. There's a high frequency orange one and a lower frequency blue one. We add them up and they propagate forwards and give us this resultant green wave. The green wave has a fixed shape. It doesn't change shape because the relative phase of the orange and blue waves is constant, because these waves are moving at the same speed, and therefore the green wave moves at the same speed as its components. A more complicated example would be if we take a Fourier integral over many different frequencies to synthesize a moving Gaussian pulse. So now we have all the different waves that we need of the right amplitudes and phase integrated together to give us a Gaussian pulse that can move in space and time. Again, this is something that does not change shape because all the different components travel at the same speed. A final example is a modulated Gaussian pulse. So that's a Gaussian pulse, it's got some sort of envelope that's multiplied by some sort of high frequency wave. And same argument, all the waves integrated together using a Fourier integral moving at the same speed gives us a pulse that does not change shape. So what I'm describing here is a situation where we have some sort of magical Fourier microscope and we can look inside and see the different harmonic waves with all their precisely defined amplitudes and phases that are just right to give us the pulse shape that we want. And all these waves move at the same speed, giving us a pulse that is constant, has a constant shape as it propagates forwards. But we know that sometimes different frequencies in a wave do not travel at the same speed, and I give you a rainbow. The reason we have rainbows is that when light waves move from air to water, they refract at different angles. They refract at different angles because the speed of the wave in water depends on the frequency. So different frequencies refract at different angles because Snell's law changes as a function of wavelength, and the colors are separated. So we know that when light is traveling through water, it does not travel, every frequency does not travel at the same speed. What this means is that the relative phase of all the different frequencies must shift as the light propagates through the water. And this phenomenon where different frequencies travel at different speeds is called dispersion. And Fourier theory gives us a really natural way to deal with this phenomenon. What we do is we break the wave up into its component frequencies, propagate each frequency at the right speed that we know from whatever relationship is giving us the speed of that wave, and then we add them up again at some later time to see what the new wave looks like, to see how it's been distorted by the fact that different frequency components travel at different speeds. So in the next few videos, what I'm going to describe is exactly this process, how we use Fourier methods to break a wave up into its component frequencies, propagate it forward, and then add it back together. Let's begin our journey through dispersive waves with a wave equation. And we're going to think about the wave equation on a stiff string. First of all, let's remind ourselves of what the wave equation is. Here it is written out for a normal floppy string like we've treated in previous courses. The T here is the tension of the string, and nu here is the linear density, kilograms per meter, if you will, of the string. And we can solve this wave equation for a harmonic wave to find a relationship between omega and k by assuming some harmonic solution, e to the I kx minus omega t. We take second derivatives in space and time and cross out the function y, and this leaves us with this equation here that says that omega squared is equal to t on nu times k squared. And this is known as the dispersion relation. A relationship between omega and k is the dispersion relation. In this case, we see that omega is directly proportional to k, so the ratio of omega and k is constant, which means the wave speed is constant, which means there is no dispersion. But now we're going to add stiffness. If we make a string stiff, and many strings are stiff, so particularly in pianos, the wires in a piano are particularly stiff, and this is an equation which can be used to treat piano strings, for example. This term here is due to the stiffness, so epsilon here is a quantity that depends on the stiffness of the string. We're not going to really try and derive what epsilon is, but it's just a parameter, a free parameter we can use to investigate the behavior of the new wave. So here's our new wave equation with this added stiffness term. We use the same trial solution. We substitute it into our wave equation, and then we have this equation here, where now we have a k to the fourth power here. We can still cross off all of the functions y, and we get a new dispersion relation. So it's a new relationship between omega and k, and now omega is not directly proportional to k any longer. In this case, the speed of the wave will change with the frequency. So if you include the stiffness of the string, you end up with an equation for the waves with an extra term in red, and the parameter epsilon is 0 for an ideal string with no stiffness and increases with stiffness. So what is the speed of the wave? So for fixed omega and k, so we choose some omega and k, then we get equations that look like this. So the speed is omega divided by k. We can re-express omega by taking the square root of both sides of this equation. So now we have c, the speed of the wave, expressed as a function of k. We can simplify this a little, and we get this expression here. So in the absence of epsilon, it's just square root t divided by nu, which is a constant. With epsilon, we see that the speed of the wave increases as k increases. Or in other words, as the wavelength goes down, the speed increases. We can also rewrite this speed in terms of omega, so we can start with this expression here and solve this equation here for omega, and we can write everything here in terms of omega, which looks a little more ugly, but there are times when you want to know what c is in terms of the temporal frequency instead of the spatial frequency. Anyway, as the limit of epsilon goes to 0 here, we can get the same constant wave speed. So the speed of the wave without stiffness is independent of k and omega, and is given by c equals square root of t divided by nu. With stiffness, the speed of the wave depends on k, or if you wish, omega, and in particular, as k increases, the speed increases, which means as lambda, the wavelength, decreases, the speed will increase. So what effect does this have on wave propagation? So let's look at the stiff string behavior using the example videos that we had earlier. So here is the pair of harmonic waves propagating together at the same speed, giving this resultant green wave, which does not change shape. If we now go to the situation with dispersion, we see that the yellow and blue waves here are propagating, but they are changing phase relative to each other because the yellow one's moving faster. So as the yellow one moves faster and moves through the blue wave, it means the sum of these waves gives this green shape, which is now changing shape as it propagates. So the green resultant wave now is no longer a constant waveform, it changes as the wave moves. What about the Gaussian wave? Without dispersion, all the wave components move together, it propagates at the speed of the different waves, which is all the same, and doesn't change shape. With dispersion, we know that the shorter wavelengths are going to be traveling faster. And so what we see is these shorter wavelengths getting out in front of the pulse, ripping the pulse apart, and it disintegrates from a Gaussian into some completely different shape. The lower frequencies being left behind and the faster ones traveling on ahead. What about the case of the modulated Gaussian? So before we had, again, this thing traveling without changing shape. And here we have the Gaussian moving, and the envelope seems to stay the same shape, but the ripples underneath are moving at a different speed. In this case, we see the envelope is moving faster than the ripples underneath the envelope. There seem to be two different velocities at play here, the velocity of the envelope and the velocity of the ripples underneath. And we'll come back to this subject of the velocity of a wave with dispersion in a few videos' time.